The direct comparison test is another test that's really pretty nice to use at times. It also gets at the idea of how quickly does the sequence go to 0. We know that the sequence has to go to 0 for it to converge, but it has to go to 0 fast enough. So the basic idea here is, suppose I have two infinite series, and the sum of the an's and the sum of the bn's, and they both have positive terms. Now, if an, I'm going back to the sequence now, is greater than or equal to bn for all n that's greater than or equal to, I'm using a capital N here for my notation, and bn, I'm sorry, that was really ugly. That's a bit better. And bn diverges, then the series an diverges. Okay, here's the idea here now. Basically what this is saying is I know what's going on with bn, and I want to know what's going on with an. So if an is greater than or equal to bn and bn diverges, then it's going to force an to diverge. Let's draw a quick picture here. First of all, if an and bn, or if an did not go to 0 to begin with, we wouldn't be checking on this. If we looked at this and an does not go to 0, then we're done. It clearly diverges. So I would use this in a situation where I take a look at the an's and it goes to 0, so it might converge. So let's just say that this is bn. And obviously it goes to 0. And what's going on is I know that this sum of all these values will actually diverge. So here I go with an's. Now remember, it said that an is greater than or equal to bn for all n greater than some cap n. So I could have a situation like this where an is actually less than this thing, and then suddenly becomes bigger, and at some point it remains bigger. Well, the point is like right here. So now I'm at this value capital N, that beyond this, an is always bigger than bn. Now, if bn diverges, then clearly, if an's bigger, it has to diverge. It's not like the squeeze theorem. It's kind of like a push theorem, which doesn't exist. I just made that up. But if the bn's converge and diverges, and an's are bigger, then it's kind of like pushing it above it. So it has to sum up to something bigger than the bn. So it also has to diverge. I mean, conceptually, that should make a lot of sense. Now, if an is less than or equal to bn's, again for all n greater than or equal to some n, in other words, at some point this becomes true, and the sum of the bn converges, then this infinite series an will converge. Whoops. Will converge. Now notice I'm not making any claim as to what it's going to converge to. I'm just saying it will converge. So let me draw a quick picture of that. So here I am. I have my bn's, and obviously it also goes to 0. And we know that bn converges. So here's my an's. I could be greater than bn, but at some point I become less than bn and I stay there. That's what this capital N is about again. At this point the an's are less than. Well, if the bn converges, then an has to converge. Adding a finite number of values that are bigger will not make this thing diverge. So if the bn's converge, it's forcing the an's to converge. Now the basic idea here is to recognize that the series you are working with is similar to some series that you already know about. That's that bn. Everything I've been talking about so far is, hey, I know what bn does. I know bn converges. So I want to compare it to an. If an is less than bn and bn converges, then an has to. If bn diverges and an is bigger than bn, then it must also diverge. Now the other combinations won't make any sense. If bn converges, but an is bigger than bn, then I still have no idea what an's doing. So let's just say, go back to this picture here. If bn converges, but AN is bigger and still goes to 0, I don't know if AN converges or not. It may or may not go to 0 fast enough. I just don't know. Likewise here, if this is my BNs, and let's just say the BN diverges, and at some point the ANs are smaller than the BNs, well, I still don't know if the ANs diverge or converge. I don't know what it's doing.